The nanometer race: how lithography defines processor performance. Defining the nanometer number. The number you see associated with a modern mobile processor, like 3 nm or 5 nm, refers to the process node or lithography. While this number no longer represents a physical measurement like the actual size of the transistor's gate, it serves as a crucial marketing and technological indicator of a chip generation's density and power efficiency. In essence, a smaller nanometer number signifies a more advanced manufacturing process that allows chip makers to pack more transistors closer together, which is the foundational concept behind Moore's law. Photolithography, the blueprint for the chip. The manufacturing process that creates these microscopic circuits is called photolithography. It is comparable to using a sophisticated, high-precision camera to print an incredibly detailed blueprint onto a silicon wafer. A complex light source, like extreme ultraviolet, or EUV, is shown through a photomask, the blueprint, and the pattern is projected, shrunk, and chemically etched onto the silicon. The smaller the nanometer number, the more challenging and precise this light-based printing process becomes. The core benefits of shrinking the node. The race to shrink the process node from 5 nm to 3 nm offers three major benefits for smartphone performance, primarily due to the transistors being smaller and closer together. First, shrinking the node leads to higher transistor density. This means more CPU cores, more powerful GPUs, and larger neural processing units, NPUs, can be packed onto the same size of silicon die, drastically increasing computational power. Improved power efficiency and speed. Second, smaller transistors require less voltage to switch states, i.e., turn on or off. This leads to a significant reduction in power consumption, meaning a 3 nm chip is inherently more power efficient than a 5 nm chip, resulting in longer battery life for the smartphone. Third, with reduced power consumption comes less heat generation. A cooler chip can sustain its high-performance clock speeds for longer periods before thermal throttling occurs, giving users better sustained performance in demanding tasks like high-end mobile gaming. The shift from FinFET to Gate-All-Around (GA), moving to the 3 nm, and especially future 2 nm, nodes requires a fundamental change in transistor design. The long-standing industry standard, FinFET, Fin Field Effect Transistor, has reached its scaling limit. The next generation design is Gate-All-Around, GA, or sometimes called MFET, Multi-Bridge Channel FET. GA surrounds the transistor channel with the gate on all four sides, offering vastly superior control over the current and significantly reducing power leakage compared to FinFET. The cost and complexity barrier. The transition to smaller nodes is immensely complex and expensive. The specialized EUV lithography machines required to manufacture 3 nm and smaller chips cost hundreds of millions of dollars each, and the process requires extreme precision and material science advancements. This high cost of R&D and manufacturing capacity means that the most advanced processors are initially reserved for flagship phones and are primarily produced by a handful of companies like TSMC and Samsung. Future of the nanometer race. The technological roadmap continues toward the nm node and beyond. However, as the size approaches the atomic scale, manufacturers are investigating alternative materials and architectures, such as nanosheets and stacking transistors vertically, to continue delivering generational improvements in power, performance, and efficiency. thereby extending the limits of Moore's law for mobile devices.